Hello, so today we're going to be doing optimization problems, and let's begin. So a cattle rancher purchased 5 150-meter rows of wire fencing to build a rectangular garden. He will use the fencing and the garden will have 4 sides. What dimensions will produce the maximum area? So first things first, we're going to draw a diagram. Okay, so we created a diagram of the garden to help visualize the problem. And then we're going to use the information in the question description to create the diagram. So, to build a rectangular garden, the garden will have 4 sides, and then what dimensions would produce the maximum area. Moving on, so use the diagram and information in the question to create equations. So we can have the area of the garden, we can have the perimeter of the garden, Okay, so we have the equation for the area of the garden, we have the equation for the perimeter of the garden, and now we're going to isolate a variable. So we're solving for the dimensions that would give us the maximum area. So what we're going to do is we're going to use this helper function. And we're going to use that to isolate a variable. To create a new function or equation that can be substituted into the area of the garden function. So this right here is a function or equation equivalent to the value of w. And what we're going to do is we're going to input the w function into the area of the garden function. That way you are only left with one variable. So again, we're going to input the w function, this function right here, into the area of a garden. And that way we are only left with one variable and can then find the derivative of the area function or area of the garden function. And then you'll find critical numbers, or x, or in this case L, values that will help you find the maximum length of the garden. So the new area function is area equals 375L minus L squared. And then we're going to find the critical numbers. So we're going to find the first derivative and set the first derivative equal to 0. And then we're going to solve for L. Those L values will be the maximum and minimum points depending on the question. Your calculated result will be substituted into this equation right here to find the maximum width of the garden. And right now we're finding the maximum length of the garden. Okay, so again, we found the derivative. We set the derivative equal to 0. We solved for L, and then we have the maximum length of the garden. And what we're going to do is we are going to substitute the maximum length of the garden into this function right here to find the maximum width of the garden. So we substituted the critical number, or the value of L, into W equals 375 minus L, or into the equation in which we isolated the variable in step 3. And then we have our width, which is 187.5 meters. So our therefore statement is the dimensions that will produce the maximum area are 187.5 meters times 187.5 meters. The length is 187.5 meters and width is 187.5 meters. It is a square and we'll use all 150 meters rolls of wire fencing to achieve the maximum area. So, that was the question. Moving on. So a rectangular pen is to be built with 1,200 meters of fencing. Sorry about that. 1,200 meters of fencing. The pen is to be divided into 3 parts with 2 parallel partitions. Find the maximum possible area. So we're going to create a diagram of the rectangular pen to help visualize the problem with the information given in the question. Okay, so we made a diagram that was of the rectangular pen. Now it's time to move on and create our functions. So use the diagram and the information in the question to create equations or functions that apply to the question. So we have the area of the pen, the perimeter of the pen, So now we are going to isolate y. So using this function here, the helper function, we will isolate y and input the result into function this function here. So we are going to input this function right here into this function right here, and then we're going to expand and multiply to get the final function, and then we're going to use that to find the derivative and then find the critical numbers. Okay, so we have our area of the pen function, and then what we're going to do is that we are going to first find the first derivative, and then we're going to set that first derivative equal to 0, and then we're going to solve for x. And then this will give you the maximum length of x, and then your calculated result of x will be substituted into this equation right here to find the maximum value of y, or the width of the pen. or the maximum length of y. So x is 150 meters. That is the maximum length of x. And then we're going to substitute this x value into this, into this equation. So y is 100 meters. That is the maximum length of y. So we substituted the critical numbers that we found, aka x equals 150 meters, into the isolated y equation. And when we did that, we found the maximum length of y. And now, or the equation in which we isolated the variable. And now we are going to find the maximum area, now that we have the dimensions in which what x is and y is worth and valued at. We can use the function a equals 3y multiplied by x to find the maximum area of the pen. As the question states in find the maximum possible area of the pen. So the area is 45,000 meters squared. It's squared because it is area and not perimeter. Area is always unit squared. So again, the area is 45,000 meters squared. So that is the, those are the dimensions that will produce the maximum area of the pen. And the maximum area of the pen is 45,000 meters squared, and then the dimensions is x equals 150 and y would equal 100 meters. And then we have our therefore statement. Okay, so the maximum area of the pen is 45,000 meters squared. The dimensions of what x and y are valued at is 150 meters and 100 meters. So x is 150 meters, y is 100 meters. It is a rectangular pen built with a 1,200 meters of fencing. Each x length is worth 150 meters long, and each y length is 100 meters long. And that's everything I have for you today. I hope that you found this helpful, and thank you very much.